in nature, alpha, beta, and gamma decays can appear in sequences. I have an example here. Those heavy elements. You know, heavy elements, they're generally not as energetically stable as intermediate-sized elements. We saw that table before, right? We saw that, you know, going up and then go down like this. So heavy elements starting from here, as it decays into intermediate-sized elements, it becomes more stable. So they split into by multiple steps into something that's more stable. Here's an example of thorium. Thorium is a heavy element, heavy nucleus, and it wants to become something more stable, lead. It doesn't do that in a single step. Okay, there is a natural sequence for it to do that. It starts with an alpha decay into radon, and then, you know, in doing so, you can see how many steps it takes in a Z. But Z does because you have emitted just you have an emitted electron, and so on. So you have a natural sequence, alpha alpha alpha. After many decays, eventually you're going to end up into lead. Now here there is a little square. What that means is that once you arrive here, you can either go this way or you can go that way. And finally, you become a much more stable nucleus, which is lead. So that's how many steps it takes to go from thorium to lead. It's a natural sequence which can take millions or even longer time to complete. Another example of a natural sequence of alpha decay is uranium-235. Uranium-235 is an element which we use in nuclear energy, whether by building a bomb or by building a power plant. But in using it as a nuclear energy source, we actually bombard it with neutrons to cause nuclear reaction. That's another matter which we'll discuss in the next chapter. If you leave it alone, it will decay. It's just a much slower process. Okay, you cannot wait for billions of years, but so that you need, you know, to bomb it with neutrons. But if you leave it alone, this is what happens. It starts with an alpha decay, and then it will also emit, then beta decay, and another alpha decay, and another alpha decay, or another beta decay. There are different ways to proceed. Eventually it becomes lead again. You can fill all the blanks yourself. For example, I did a couple examples for you. You start with uranium and alpha decay. What is this? Well, this is a nuclide with an A number of 231 because you lost 4 nucleons, right, through alpha decay. And it's got a Z number of 90 because you lost 2 positively charged protons, so that becomes 90. So that's an example, thorium. And then you go beta decay, you lose an electron, so you know, so the Z number goes from 90 to 91 because you lose a negative charge particle, you just simply gain a positive charge particle, and so on. And so this is the new element that you get. You can consult elementary table and look at what alpha and beta decay does for you, and you can fill all these blanks. It's fun to do that. All right. Now, as a prelude to the next chapter, which we deal with nuclear energy, let's look at nuclear reactions. In a nuclear reaction, you don't just let this thing decay by itself. Rather, you bombard it. You bombard a target nucleus with another particle. This particle is called A. So A strikes the nucleus target B, which turns it into X, and it turns into another nuclide Y plus some other particle B. For example, here is a lithium-7 target nuclide. You bombard it with a proton, and it will split into 2 alpha particles, or 2 helium nucleus or nuclei. That's an example. Okay, this type of nuclear reaction cannot just necessarily take place. You have to look at what's called you have to look at the energy that comes out of it, which can be positive or negative, in fact. Again, you start with the total mass before the reaction minus the total mass after the reaction, MF. The difference is the energy that's lost And that energy lost, if it's positive, that means part of the rest energy actually turns into rest mass actually turns into energy, and this reaction can happen spontaneously. Okay, it will just these particles will lose part of their mass and turn them into energy. So spontaneously. If A is close to X, that's going to happen. Okay. On the other hand, if Q is negative, that means the final rest mass is greater than the initial rest mass, which means you have to feed some energy into it. Otherwise, where does the excess mass come from? Excessive mass corresponds to excessive energy, right? Who gives it energy? Well, it must be the bombarding particle, A. A should come in with sufficient amount of kinetic energy to trigger the reaction. That kinetic energy does a double duty. First of all, it provides the gain in rest energy, so the final mass can be greater than initial mass. The difference is the energy that's provided by the kinetic energy of the particle A, and B, the kinetic energy of this incoming particle A must also be partly converted to the kinetic energy of the final particles. The final particles cannot be both at rest. If they're both at rest, you will have no linear momentum afterwards. But before the collision, this guy has kinetic energy, therefore it must have some linear momentum. In order to conserve linear momentum, part of the energy that's brought in by this guy must be converted into the final kinetic energy that both guys will be moving. Okay, so therefore the kinetic energy of the incoming particle for this case must be greater than Q, than the absolute value of Q. Okay. This is called endothermic reaction. It will not happen by itself unless the incoming particle has a minimum amount of kinetic energy, which we call E threshold, ETH. TH means threshold. It's threshold energy. And we're typically talking about MeV, order of MeV. Let's look at what kind of threshold energy is necessary to trigger an endothermic nuclear reaction. This is the minimum amount of kinetic energy that this guy must have in order to initiate this nuclear reaction. And I'm going to make an assumption here. The assumption is that after the collision, the entire thing, B plus Y, move in one piece. They have the same speed. This, as in physics 1A, it's an example of a complete inelastic collision, right? These guys do not have different speeds. Now, why do I make that assumption? This is not a groundless assumption, because I'm looking for the minimum amount of energy, kinetic energy, this guy has to trigger the reaction. Now, remember, you have a certain amount of momentum, right? This guy has no momentum. So the final momentum carried by both of them must be the same as this PA. Now, you want this momentum because you have to consider momentum, but on the other hand, you don't want this final particle to have too much kinetic energy because you don't have a lot of kinetic energy to begin with, right? You want to convert most of this kinetic energy into what? Into Q, right? Into rest mass. Okay? So how do you keep the same momentum while minimizing the kinetic energy associated with that momentum? Well, simple, because the momentum is related to the energy like this. K equals P squared over 2m. That's 1/2 mv squared, assuming non-relativistic speeds, which is true for these massive particles. So this tells us for the same momentum, the greater the mass is, the less the kinetic energy it possesses. Okay, now what's the greatest mass possible after the collision? The whole thing, right? So if the whole thing carries the same speed, they move as a single piece, then for the momentum it has the smallest amount of kinetic energy, which makes the incoming particle as less energetic as possible. That is threshold energy. Okay, good. So we argued why a complete inelastic collision is the case here. Here is the kinetic energy of the incoming particle. That is by definition threshold energy. Q is initial mass minus final mass times c squared, and it is negative. Okay, it is negative. So the change in energy is 0, which means the kinetic energy of the incoming particle plus the rest energy of the initial particles must equal to the kinetic energy of the final particle plus the rest mass of the rest energy of the final particles. Okay, PA and PA are the same. I already used conservation of linear momentum. So I'm going to move this term over here and take out PA. And then that term here, I'm going to move this term over here, and this by definition is negative Q. Q is itself negative, so negative Q is actually positive. Okay, so you do some little algebra, and you have this ratio here. This is E threshold, which is we're looking for. MB plus MY, that is the final rest mass. It is roughly equal to the initial rest mass, roughly, okay, because the, whatever. Initial and the total rest mass final, they're roughly equal to each other, so this is just difference is mx. So you can replace this ratio with that ratio. And then this is E threshold, you move that over, and here is your result. Okay, absolute value of Q times this ratio. This is 1 plus something, so it's greater than 1. So therefore, indeed, you need, then the incoming particle must have a minimum amount of kinetic energy which is somewhat greater than Q, because part of that kinetic energy must go to the final kinetic energy. We give it as little as possible in the threshold case, but still that's greater than Q. That is the formula that you wanted to prove in problem number 58 of this chapter. As a final example of this chapter, let's look at NMR and MRI. NMR stands for nuclear magnetic resonance, and MRI is a related term which we use primarily in medical imaging. Let's look at NMR, which is the physics behind MRI. The atomic nucleus is made of a bunch of spin 1/2 particles. Each has an angular momentum. You can add all these angular momenta up, all these protons, neutrons, add all their angular momenta up. You get a combined angular momentum, spin angular momentum for the entire nucleus. And the quantum number, we call it I. I can be the integer or a half integer. Okay, so this is the angular momentum of the nucleus due to all the spins of the constituent nucleons. And if you know the quantum number I associated with that angular momentum, then the magnitude is always like this. This is for all angular momenta in quantum mechanics. However, this angular momentum, how does it associate with a magnetic dipole moment? Remember, spin, or whether it's electronic spin or electronic orbital motion, the angular momentum associated with the spin or orbital motion, they both can be converted to some sort of a magnetic dipole moment, right? They're associated with a magnetic dipole moment. And in the case of electrons, you just multiply the angular momentum by what's called a Bohr magneton, right? To get the associated magnetic dipole moment due to that angular momentum. The Bohr magneton is equal to EH bar over 2me, mass of the electron. Now here we replace the electrons with nucleons, so we have to replace this mass of the electron with the mass of a proton or a neutron, pretty close to each other, and that is about 1/2000th of the mass of the it's 2,000 times roughly the mass of the electron. Therefore, mu b is about 2,000 times mu n. Mu n is not called Bohr magneton anymore. Rather, it's associated with the atomic nucleus. What that means is that the energy gap due to different angular momentum, when you expose the atomic nucleus to a magnetic field, you're going to get energy split, right? The energy split is negative mu dot b, but this mu, you replace the Bohr magneton, mu b, with mu n, which is about 1/2000th of mu b. You're going to get a much smaller energy gap, much smaller energy gap. Okay, and here's the formula, mu n, which is about this much, 10 to the negative 8 eV per Tesla, times mz. What's mz? mz is the z component of this angular momentum of the nucleus, times b. b is along the z direction. Okay, mz, what's the possible value of mz? It depends on what I is. Here's an example of I equals 3/2. Okay, then you have 4 possible values of mz because the highest value is 3 over 2, and it's 3 over 2 here. Next is 1/2, and then negative 1/2, and negative 3 over 2. These are the 3 possible values. It's 2i plus 1. These are the possible numbers of z components. Just as usual. Okay, so when you expose this nucleus to a magnetic field, you find that you have this additional term of energy, negative mu dot b. So mz has 4 different values, from this value to that value, and therefore it's going to split the energy 4 ways with adjacent energy gap given by negative mu n times b times the difference in mz from one number to the next number, and that's 1. Okay, that's 1. So therefore the order of magnitude of the splitting is of the order of mu n times b. Okay, this being 1, mu n times b. Mu n is this much. Okay, it's 3 orders of magnitude lower than mu b times the magnetic field. If the magnetic field is about 1 Tesla, then we're looking at 3 times 10 to the negative 8 eV. This is very different when you expose an electron to the same magnetic field. You're looking at energy gap of 3 times 10 to the negative 5 eV. This is negative 8 eV, much less. Okay, and you compare that with a 3 eV. This is 3 times 10 to the negative 8 eV. Compare with a 3 eV visible light. Okay, in order to get 3 eV of visible of energy, a photon must have a frequency of 10 to the 14 hertz. If you only need 3 times 10 to the negative 8 eV, that photon will only need 10 to the 6 hertz, because we're talking about 8 orders of magnitude difference. Okay, 16 minus 8 equals 14 minus 8 equals 6. So 1 megahertz, that's enough. 1 megahertz. What kind of photon is that? That is not visible light. It's not even infrared or microwave. It is radio wave. 1 megahertz, typical radio wave. You know what that means? It means that if the nucleus originally is at this state, I can give it let it absorb a photon, can jump over here. This photon energy is of the order of 1 megahertz, which means, the frequency is of 1 megahertz, which means it's a radio frequency. If I expose this nucleus to a radio wave of the proper frequency, it will allow it to jump from one level to the next level. Okay, if the frequency of the radio wave matches that energy difference, then you can have a frequent jump from here to there. That is a resonance called nuclear magnetic resonance. Make sense? Nuclear magnetic. It's the from one level to the next. When you expose it to 1 Tesla field, you're looking at a photon which is 3 times as energetic. 1,000 times as energetic as this. Okay, what are the possible applications of nuclear magnetic resonance? Well, one of the most prominent applications is in medical field, medical imaging technology, MRI. MRI stands for magnetic resonance imaging. Behind it is NMR. Now, we don't call it NMR in medical terms because the term nuclear, N, can scare away some patients, even though, there is no radioactivity involved at all, okay? Just flipping of nuclear spins in a magnetic field. Molecules. Okay, you have a lot of water molecules. Inside the water molecule, you have the hydrogen, 2 hydrogens, and they have protons, and this proton has its own magnetic dipole moment, and you expose it to a magnetic field around 1 Tesla. It's going to split 2 ways. Okay, spin up and spin down, split 2 ways, and the energy gap, HF, the corresponding photon frequency, which will cause the energy difference, is about 10 to the negative 8 eV, which means F is about 1 megahertz. Okay, so this radio wave can cause the spins to flip, and therefore this radio wave at this right frequency will be easily absorbed by the protons in the H2O molecules. So here is the basic diagram how it works. You expose the the imaging area, such as your brain or your knee, to a magnetic field. This magnetic field is large, it's about 1 Tesla, and it is not uniform. Okay, it varies from here to there, hopefully in a very simple form, such as a straight line from place to place. And then you have a radio wave source coming in. Radio wave is harmless. Now, I'm going to draw something here, okay? So suppose you want to do an imaging of this guy's brain. Okay, this is his brain, right? We want to see what's going on. The brain, of course, the brain tissue has a lot of water molecules in it. You have radio waves coming in, and you have radio wave detector after it passes through the brain. If these photons are heavily absorbed by the water molecules here, as the protons in the nuclei of the water molecules spin, change their spin from one state to another, then you're going to detect much less intensity, right? And then the lower the intensity you get, that means the more of these water molecules are available to flip the spins and absorb the energy, which means the tissue density is higher. The tissue density is then turned into a map by the computer, which you can see visually. You can get an image of what's going on inside the brain. Now, how do you figure out which part of the brain we're talking about? Very simple. If you want to study this slice of the brain, this slice of the brain corresponds to this much B value. Okay, a given B value, because B is a function of location X. And in order to flip the spins of the water molecules in this area, we have to supply it with the right amount of radio frequency. So HF equals to the change in delta U, which is mu n times B. At that location, that's the same formula here, right? And we know what B is as a function of X. And so we have a frequency coming in. This frequency is heavily absorbed here, which means there's resonance going on, all the spins are flipping. And by knowing what F is, I can find B. And from that B, I can know which part of the brain we're talking about. This is the X value, so you know the location of this slice. Okay? Or, you can also change the value of B. Also, you can change the value of F by fixing B, so you can also know which part of the brain we're talking about. So this is the basic idea behind MRI. Instead of CT, in which case you're exposed to a highly energetic photon called X-ray, we're exposing ourselves only to the harmless static magnetic field, as well as radio wave photons. But of course, MRI cannot totally replace X-ray, because X-rays are useful for examining bones, because X-ray photons do not pass through the bones easily, but they can pass through soft tissues, so you can get a structure of the bones. With MRI, again, if you have a lot of water molecules in the area, soft tissues, this is a good technique, better imaging technique than X-rays. In the next chapter, we're going to focus primarily on how to harness nuclear energy through nuclear fission and nuclear fusion. We're going to zero in on that particular aspect, the most important aspect of the applications of nuclear physics. And that's in the next chapter.